This is Rebecca Raphael, Lab M03, with my Lab 3 constant velocity motion report. I made an observation and took a video of a car moving at a constant speed. I modeled it, and the assumption F net equals 0 provides good predictions of the observed motion. Here's the clip of the car. I set the start frame after the car started moving and ended it when it was still going the same speed. I set the origin of the coordinate system at the center of the front wheel of the car and had the positive x direction aligned with the angle the car was moving at. I also found the dimensions of the car online and set the calibration stick to 4.796 meters. I used the center of the front wheel as the average position point because it was the easiest to mark in the same position every frame. The time between frames was about 1/30th of a second, and the total time was about 0.5 seconds. To predict the motion, I needed the mass of the car, which I found online as 1,329.933 kilograms, the initial position of the ball, which I got from the analysis, xi equals 0.0065 meters, and the velocity, which was found by taking delta x over the entire video clip, which gave 2.47 minus 0.0065 over 0.5 minus 0, which equaled 4.93 meters per second. For the model prediction, I started at t equals 0 and ran it until t equals 0.5 seconds. I set a delta t of 0.00001. Since the final velocity is equal to the initial velocity, the second term, f net over m times delta t, must equal 0. Because the mass and time are not equal to 0, f net must equal 0, and this is how the motion can be predicted using Newton's second law. Here's the motion. The ball starts slightly to the right of the origin, and it moves to the right as time increases because the axis I selected made the car travel in the positive x direction. The graph shows this trend as well. I plotted the model data and the experiment tracker data on the same graph in order to compare them. The data I collected from my observation using the tracker video is shown by the blue diamonds, and the model data is shown by the red line. The graphs show position versus time, and as you can see, the two lines have the same trend. If you made a different choice of origin, the position would change, but the velocity would not. For example, if the origin is moved to the edge of the car, then the x values increase. Also, if the origin is rotated, the direction may be changed, such as if you had it going in the negative instead of positive x direction. This would also change the sign of the velocity, but the value would remain the same. What does it mean? Is it possible for you to say how many pushes and pulls are added together to give 0 net force in the case that you observed? The answer is no. There isn't enough data to find how many pushes and pulls are added together. It is only known that they are equal to each other because the velocity is constant. If the velocity weren't constant, then the F net would not be equal to 0.